Okay, so quick review about prime numbers. A prime number is any whole number greater than 1 whose only factors are 1 and itself. For example, 2 is a prime number because it's 1 times 2, and that's it. This is the only pair of factors for 2. In other words, the only pair of whole numbers that you can multiply together and make 2. 7 is also a prime number because it's 1 times 7, and again, that's it. There are no other whole numbers that you can multiply together to make 7. On the other hand, 6 is not a prime number because it's 1 times 6, but it's also 2 times 3. And so because 6 has factors other than just 1 in itself, 6 is not a prime number. 20 is 1 times 20, it's 2 times 10, and it's 4 times 5. So 20 has several factors other than just 1 in itself, so 20 is not a prime number either. Now, a minute ago I said that a prime number is any whole number greater than 1 whose only factors are 1 and itself. So why greater than 1? I mean, if you think about it, 1's only factors are actually 1 and itself. So it sort of seems like maybe 1 should be a prime number, but it's not. We actually specifically exclude 1 from the definition of prime numbers by saying that prime numbers have to be greater than 1. And we do that for a very good reason, because 1 does not behave the same way as prime numbers behave. It's not really useful for the kinds of things that prime numbers are useful for. And I think you'll see what I mean in just a minute. What we're actually here to talk about is prime factorization. Prime factorization means taking a number and breaking it down into its prime factors. And we can do that by making something called a factor tree. We're going to make a factor tree for 24. And to start, we just need any pair of factors for 24, any pair of numbers, pair of whole numbers, whose product is 24. So for example, 6 and 4. 6 times 4 is 24. But we're looking for prime factors, and 6 and 4 are not prime. That means that we can break them down into their factors. 6 is 2 times 3, and 4 is 2 times 2. 2 and 3 are prime numbers. So I'm going to go ahead and circle them. And what we want is for every branch to end at a prime number. Eventually, they will. No matter how big your number is, no matter how many factors it has, eventually every branch will end at a prime number. Here, it only took a couple of branches. And we get 2 times 3 times 2 times 2. Or it's usually better to write that in order from least to greatest. So I'm going to write that 2 times 2 times 2 times 3. It's the same thing, just in order from least to greatest. This is the prime factorization. The prime factorization of 24. And what that means is it's a group of prime numbers whose product is 24. In other words, if you multiply these all together, you get 24. And believe it or not, it is the only group of prime numbers whose product is 24. There is no other group of prime numbers that you can find that you can multiply together and get 24. And that's actually one of the things that makes prime numbers really interesting. Every whole number, if it's not prime itself, only has one prime factorization. And if it is prime itself, then its prime factorization is just itself. Let's try another one. Let's try 60. 60 has lots of factors. So there's quite a few different ways we could start here, but how about 6 and 10? 6 times 10 is 60. But 6 and 10 are not prime. 6 can be broken down into 2 times 3, and 10 is 2 times 5. Now, 2, 3, and 5 are all prime numbers. And so we get the prime factorization of 60. 2 times 3 times 2 times 5, or 2 times 2 times 3 times 5. That is the prime factorization of 60. It is the only group of prime numbers whose product is 60. Let's do one more example, and then I'll show you something pretty cool you can do with this. Let's do a bigger number, like 108. Now, if you really, really know your multiplication facts, you might remember that 108 is 12 times 9. But if not, don't worry. I'll show you what else you can do in just a minute. Now, 12 is not a prime number, so we'll keep going. 12 is 6 times 2. And 9 is not prime either. 9 is 3 times 3. Now, 3 is prime, and 2 is prime, but 6 is not. So we'll keep going with the 6. And 6 is 2 times 3. Both of those are prime. So now every branch ends at a prime number, and so we're done. We get 2 times 2 times 3 times 3 times 3. Now, maybe you look at a number like 108 and you don't know right off the top of your head that that's 12 times 9. But maybe you do notice that it's even. 108 is an even number. And that means that it's 2 times something. And maybe you could do the division, or just try to cut it in half in your head, or do however you want. Eventually, you would figure out that 108 is 2 times 54. Now, 2 is a prime number, but 54 is not. 54 is 9 times 6. Now, 9 and 6, neither one of those is prime, so we can keep going. 9 is 3 times 3, and 6 is 2 times 3. And these are all prime numbers down here. They're all 2s and 3s. And so now every branch ends at a prime number. This branch was really short, but it does end in a prime number. And what we get is 2 times 2 times 3 times 3 times 3, which is exactly the same thing we got up here. So even though these two factor trees look completely different because we broke the number down in completely different ways, we end up with the same prime factorization. And no matter what you do, you always have to end up with the same prime factorization because it's the only one that exists. There is only one prime factorization for every number, including 108. So no matter how you do it, it's going to be the one that you get. Now, the only thing you don't want to do is use a 1. If you use 1, you could do things like 108 is 1 times 108. And then you could say 108 is 1 times 108. And then you could just do that forever. You could even say 1 is 1 times 1, and you could do that forever. And so you can sort of see what the problem is. Our factor tree would never end, and our prime factorization would never end, because we'd have all these 1s. But all of the interesting stuff would still be this over here. This part would not be different. The only difference would be you would have an endless supply of 1s in your prime factorization. And that's kind of what I meant when I said 1 is not really useful for the kinds of things that prime numbers are useful for. If we allowed 1 to be a prime number, and if we used it in our prime factorizations, Our factor trees would never end. Our prime factorizations would never end. And our prime factorizations would no longer be unique. There would no longer only be one for every number, since we could just add a 1, or add 2 ones, or add 3 ones, or add however many ones that we want. So it's better to just say, well, 1's not a prime number because it doesn't act like a prime number. Okay, so this is cool enough, but let me show you something else you can do. It turns out that every factor of a number is actually hiding in its prime factorization, not just the prime factors. So let's go back to our prime factorization for 60 from a minute ago, which was 2 times 2 times 3 times 5. Now, I actually have that written down on little separate pieces of paper so that we can move them around and put them into groups. And that's exactly what we're going to do. We're just going to put some of these in one group and some of them in another. Altogether, they're 60. 2 times 2 times 3 times 5. But if we put them in groups, we can find other pairs of factors for 60. For example, 2 times 3 is 6, and 2 times 5 is 10. And so we get 6 and 10. Well, 6 times 10, that's 60. That's a pair of factors for 60. Or we could do this. Okay. 2 times 2 is 4, and 3 times 5 is 15. And so 4 times 15, well, yeah, 4 times 15 is 60. Or what if I put all of these together and I just left this one by itself? Well, 2 times 2 times 3, that's 12. 5 is just 5. And 12 times 5, yeah, that's also 60. And no matter how you do this, you will get a new factor pair for 60. And if you do it enough, you'll find all the factor pairs for 60. And so because all of the factors are hiding inside the prime factorization, there's one other cool thing I want to show you. Let's take that prime factorization for 60 one more time. And let's also take the one that we found for 108, which was 2 times 2 times 3 times 3 times 3. And if you look at these, you'll notice they actually have some things in common. They both have a 2. They both have another 2. They both have a 3. And it doesn't really matter the order. I could have picked this 3 instead. But what matters is that the factors, the prime factors that they have in common are a 2, another 2, and a 3. And if we multiply those together, 2 times 2 times 3, we get 12. And so think about what that means, okay? It means that 12 is a factor of 60 because it's contained inside its prime factorization. And it means that 12 is a factor of 108 because it's contained inside its prime factorization. So 12 is a factor of 60, and it's a factor of 108. And since these two prime factorizations don't have anything left in common, that actually means that 12 is the biggest number, which is a factor of both 60 and 108. Now, it's not the biggest factor of 60, and it's not the biggest factor of 108, but it is the biggest number, which is a factor of both numbers. And that means that it's the greatest common factor. And that's awesome. I think this is the easiest and most natural way to find the greatest common factor of 2 or more numbers. It's definitely easier than listing out all the factors of 60 and listing out all the factors of 108, or using these methods where you divide both numbers by something over and over again, like you're reducing a fraction or something like that. You don't have to find all the factors. You don't even have to know all the factors at all. You just have to make a factor tree and see what they have in common.